In this video, we're going to be discussing the binomial distribution, but we begin with the Bernoulli distribution. In particular, a Bernoulli trial, sometimes called a binomial trial, is a random experiment with exactly two possible outcomes, success and failure. And the probability of success is the same every time the experiment is conducted. Since a Bernoulli trial has only two possible outcomes, it can be framed as some yes or no question. For example, did the structure fail to operate as designed? Yes or no. Did the drug cause side effects? Yes or no. So therefore, success and failure are simply labels for the two possible outcomes, and they shouldn't be taken literally. The term success in this sense means the conditions, whether they're good or bad, that we were looking for have occurred. So if we are looking for chemicals that may cause tumors in rats, having a tumor would be called a success. Failure means those conditions did not occur. The Bernoulli distribution is very useful for modeling a risk event that may or may not occur. So let's consider an example here. In particular, the probability of winning a game against your top rival is 50%. You're evenly matched. So here is a Bernoulli distribution. Generally, we assigned x equal to p for success and x equal to 1 minus p for a failure. Hence, the single parameter for the Bernoulli distribution is the p that you see there in the upper left corner. Once you know what p is, you have completely determined a distribution. So once we know that p is 0.5, we know that these are the two outcomes. If the outcome of the trial is a success, we set x equal to 1, and in this particular distribution there's a 50% chance of a success. And if it's a failure, we set x equal to 0, also a 50% chance. Keep in mind, of course, that we can change these. This can be any value between 0 and 1. And there we have a Bernoulli trial. Let's move on now to the binomial distribution. And we begin here with the mass distribution function and the cumulative distribution function. Notice that we now have two parameters, n and p. X, of course, would be the data. So a binomial experiment, also called a Bernoulli trial, it's a statistical experiment that has the following properties. The experiment consists of n repeatable trials. Each trial can result in just two possible outcomes. One of these we call a success, the other is called a failure. The probability of success, denoted by p, is the same on every trial, and the trials are independent. That is, the outcome on one trial does not affect the outcome on other trials. So let's illustrate this if we can. Let me come down here to an empty cell. We'll enter a binomial distribution in here. And we're going to use this where we're playing 10 games against the rival team, and the probability of winning any one game is 0.5. Whoops. Let me try that again. So this distribution right here is a picture of what can happen playing 10 games. You might win 0. There's a very small chance of that. You might win all 10. There's a very small chance of that. You can see the most likely number of wins is 5, and coincidentally 0.5 times 10 is 5. So let's illustrate the properties that we just identified with this example. So we're playing an opponent in 10 games, and we're so evenly matched that the probability of winning any one game is 0.5, and that never changes. This is a binomial experiment because The experiment consists of repeated trials. We're playing 10 games, so n equals 10. Each trial can result in just two possible outcomes: win or lose the game. The probability of success is constant at 0.5 on every trial or every game, and the trials are independent. Winning one game does not affect whether you win any other games. So once again, keep in mind now, because if you're new to this, it can be confusing. This P, this probability, is the probability of winning any one event. We have here another probability. This is the probability of the outcomes that you see. So we have a probability of no games is very small. 2 games is about 4%. The probability of winning 3 games is about 12%. And so it will go. One of the most useful applications of the binomial distribution is that it helps us identify things that are weird. Now, that's not a very scientific term, but I like to use it because it's so descriptive. So here are some examples to consider. We're going to look right in here, and we're going to look at a number of examples. Beginning with, your home team wins no games out of 10 to a team they beat 50% of the time. Would that be weird if that happened? Or how about this? You get 2 faulty pieces of equipment in a shipment of 20 pieces of equipment from a supplier where the equipment is flawless 80% of the time, or where it is flawed 20% of the time. 5 of 7 of your children are boys. Is that strange if 50% of all children are boys? Would it be weird if you have 3 shortfalls in your cash register receipts in 30 shifts, if shortfalls normally occur 1% of the time? If the average success rate for selling to a customer is 75%, would it be weird if you completed a sale 9 of 12 times? Suppose you find malignant tumors in 18 of 46 rats, and the background rate for tumors is only 5%. Would that be weird? Or, finally, suppose you find 40 of 100 fish are dead when mortality rates are expected to be 15%. Well, let's take a look at this. I'm going to scroll on over, and we can see here I've calculated these probabilities. The probability of this event right here is 0.0009. And so if we're going to talk about what's weird, we know that these things could happen. What we want to know is if it would be weird if they did happen. So how can we determine if something that happens is weird or not? We can use probability. Deciding what's weird is a subjective judgment, though. So for the moment, let's say that something that happens 5% of the time or less is weird. Then that clearly makes this outcome of you winning no games out of 10 weird. When something like this happens, we have a basic choice to make. We must decide which is more likely. Did we just see something weird happen? Winning 0 out of 10 games to a team that we beat 50% of the time? That could happen. It has a probability there. It's a very low probability. So if it happens, it would be very weird. Or is there a better explanation for what happened? And the better explanation would be, perhaps we're no longer evenly matched. Perhaps we no longer have a probability of winning of 50%. Maybe the other team has gotten better, or we've gotten worse. So when you look at something that has a 0.0009 chance of occurring, you have to decide which is most likely to have happened. Your team has gotten worse, or this was just an incredible string of bad luck. We would continue the idea, getting 2 faulty pieces of equipment in a shipment of 20. There's a 13% chance of that. If that's something that happens 13% of the time and we use 5% as the cutoff, then we'd say that's not weird. 5 of 7 children being boys, there's a 16% chance that that would be the outcome if you have 7 children. How about the shortfalls in the cash register? That's well below 5%. This might suggest either that something very weird has happened, it was just dumb bad luck, or something else. That something else might be that employees are stealing from the cash register. Completing 9 of 12 sales when the success rate is 75%, that's not weird at all. There's a 26% chance that would happen. If we had 46 rats that were consuming a chemical that was not in a control group, and 18 of them ended up with tumors, when 5% is the expected rate, we see that would be extremely weird. That's 10 to the minus 12 weird. It would be very difficult to justify believing that we just, by dumb luck, had 18 of 46 rats with tumors, and the background rate really is 5%. It's more likely that the chemical that these rats were consuming is causing cancer, and the background rate for those animals consuming this chemical is much greater than 5%. And finally, 40 out of 100 fish are dead when mortality rates are expected to be 15%. That also is very weird. So either we were dumb lucky or perhaps the mortality rate has increased. Okay, so one thing I would like you to understand is these probabilities help us understand if something is as expected or not. It's useful to be able to identify weird things so they can be understood and so we can explain them. Unusually bad things we would like to eliminate. Unusually good things we want to duplicate. The binomial distribution helps us identify weird things, and that's very helpful to many risk assessments. The uses of the binomial distribution in risk assessment are endless, and I believe it's the single most useful distribution to know and understand. It's very valuable for modeling natural variability in the world, so let's have a look at how that works. Up here, we've calculated a probability, and oh, by the way, there's a binomial distribution formula that's available in Excel to do that. But for now, that's not going to be our concern. What I would like you to see here is the variability in the world. If you have a 50% chance of beating a team, this is a picture of all the possible outcomes, and our outcome was this one. It's possible, could happen, we were just so unlucky and it happened, or we are no longer the team that we thought we were. Let's take a look at those faulty pieces of equipment. 20 pieces of equipment get sent. You can see here, this is a picture of the variability in the world. These are the things that could happen. Clearly, this is the most likely thing that would happen, that there would be 4 defects. We had 2, and that has that 13% chance of occurring. Not so terribly weird. Again, we're looking at the variability that the binomial distribution displays for us. If you had 7 children and there's a 50% chance of having a boy, these are the outcomes. No boys, all boys. We had 5 boys, and that is not so terribly weird. This time we're looking at 30 different shifts in our store, and we are looking at 3 shortfalls in cash. There's 1, 2, 3. That's this value right here. That's a very small probability, and it looks like it's a bit unusual. So either something dumb lucky just happened to us, or there's another explanation. But once again, this shows you all the things that can happen from 0 shortfalls through 30. So this distribution, this binomial distribution, gives us a nice view of the natural variability in the world. Here we have 12 different customers calling, and there's a 75% success rate on each. So if we take a look here, this is the most likely outcome. It's 9, and that's what we got. That's the 25% outcome. So even though you would expect 75% of all customers to buy, and 9 is the most likely, that's not a 100% likelihood. There's variability in the world. We could have 10. We could have been a little lucky. We could have 8, a little bit unlucky. So, again, I repeat, this is the variability that's present in the world, and the binomial distribution does a great job of displaying it for us. These are the 46 different rats. And we're looking at 5% background of tumors, and 18 rats got tumors. That's an incredibly small number. It looks like there might be a better explanation for this than that we were just dumb lucky. And finally, for our 100 fish, we had 40 out of 100 that died, and you can see that also is incredibly unlikely. But what this binomial distribution has done for us is it showed us the variability in the world, the range of outcomes from no fish die all the way up to all of them die. Now we have one more look at the binomial distribution, and this is a very simple model here, simulating the results of receiving a shipment of 100 fragile light bulbs. So suppose the breakage rate is 2%. And we always receive 100 light bulbs. 2% of 100 is 2 light bulbs, and that's what we would expect over the long run. But would we expect that with every shipment? Would we be surprised, or another way of saying that is, would it be weird if we got 3 broken bulbs in a shipment? Or 4 broken bulbs in a shipment? And I would be inclined to say, no, that doesn't sound so weird. That just sounds like we're a little bit unlucky. But how about a shipment with no broken bulbs? Would that be weird? No, that sounds like we were just a little bit luckier than average in that situation. So if we want to build models that help us show the natural variability in the world, the binomial distribution is seen here as a very useful distribution for modeling variability. Let me show you how that works. Here's the 100 light bulbs. Here's the 2%. In this cell right here, we have a binomial distribution. The N is found in A2. That's the 100 light bulbs. The B1 is found the probability is found in B1. And this is a picture of all the potential outcomes, from all 100 are broken to 0 are broken. And you can see here, with our Monte Carlo process turned on, in this particular shipment, there were 3. In this shipment, there were 2. There's a shipment that had 1. There's another 1, and a 3, and a 1, and a 5, and a 0. And so each shipment has a different number, but they never get too far away from the expected value of 2. If they did, we might suspect that perhaps the defect rate is no longer 2%, that maybe something's happened to quality control with this company. So once again, if you were going to be building event trees, and we will be building event trees in our next class, this binomial distribution is great as a switching function. And that is a term of my own invention, and it basically means we have 100 light bulbs that arrive here at this node. Some of them will be broken, some of them will not be broken, and we use the binomial distribution to figure out how many go this way and how many go that way. Thus the binomial distribution is kind of controlling the switch here.